Alright, so we're going to start one-dimensional motion. In other words, we're just moving forward and backwards. We're not going left and right, so to speak. We're just going forward and backwards to start out with. But before we even get started with that, we need to talk about some basic definitions. First off, what is a vector and what is a scalar? So a vector is a measurement with a direction. So if I am going to go 3 meters north, that would be a vector, where a scalar is just a measurement, 3 meters. Another example of vectors, not only can you give it a direction, 3 meters north, or maybe you say 3 meters, and I'm going to use the yet symbol here, 30 degrees, that would also indicate a direction. You could also indicate it with a positive or negative. Negative 3 meters would imply backwards, or positive 3 meters would imply forward. So if you actually put down the positive or negative in front, that would make it a vector, where just writing 3 meters would be a scalar. Now, there are some measurements that have no choice. They are always scalars. For example, temperature, right? It is 20 degrees Celsius. Well, that's just a number. That's just a scalar. There is no direction. With temperature, that's possible. You can't make that into a vector. A few other different things that are applying this concept. Distance is just how far you travel. It's a scalar. Its partner, if you will, that we will use all the time is displacement. Straight line distance from start to end. So distance might be this blue curve you run in cross country all throughout the race, all throughout the woods, going everywhere, all the way start to end. And displacement, if you will, is maybe saying is as the crow flies. Straight line distance, start to end, with a definite direction, and then the shortest distance possible, I guess you could say. Speed, how fast you are going. That's a scalar. Velocity is speed in a direction, a vector. And you have a couple of very basic equations for velocity. Velocity is displacement divided by time, or change in position divided by time. Displacement is a change in position from start to end. So anytime you see this triangle here, that's Greek letter delta. Greek letter delta can be broken down into final position minus initial position, or final velocity minus initial velocity. Delta means change in, which is always the final minus the initial. So that's why these two equations are the exact same thing. Make sure you get those equations down. Those are very, very basic ones, plug chug. You should have seen those at some other point in time in your educational career. Acceleration, likewise, is a change in velocity. So change in velocity, it's a vector, right? Another way to write that would be acceleration is the final velocity minus the initial velocity divided by the time that it takes. Now there are actually, if you will, 3 ways that you could be considered accelerating, because velocity is a vector. That means it has a specific direction to it. So you could be accelerating if you, quote, are speeding up, or if you are slowing down, or if you are changing direction. Because if you are changing direction, right, velocity is a vector, it has a specific direction. So if you are changing direction, you are changing your velocity. So speeding up, slowing down, changing direction would be a change in velocity, thus you are accelerating. Now you'll see a few problems for us that just involve these very basic velocity or very basic acceleration equations, but we're really going to hit those and move right off, so we're not going to be spending much time with that. 3 types of velocity that I do want to mention right now, and we're going to come back to. Constant velocity, meaning that the velocity stays the same the entire time, flatlining, if you will, on a velocity time graph. Average velocity is whenever the velocity is changing all over the place, like this blue curve, and you average it out. Now, the best way to take the average velocity isn't to try to count all these individual points, because we know in a line there's an infinite number of points, and then divide by the number of them. That's really a more difficult task. Instead, you just take the, if you're trying to get an average velocity, just come back to this equation. This is technically the constant velocity equation over here, but it works for average velocity as well. What is your total displacement? Your final position minus your initial position, divided by how long it took, and you've got the average velocity, even if it was changing all throughout. Instantaneous velocity is how fast you are going or what is your velocity at that exact moment. So let's say we were looking for how fast you were going at 3 seconds, if this was measured in seconds over here. So you trace up to the graph, and there that is. Come over to whatever that velocity is. Oh, let's just make it up. Let's say it's 2 meters per second. That would be your instantaneous velocity at that moment. Alright, so getting off those very basic equations of velocity equals change in displacement over time and acceleration equals change in velocity over time, those are things you probably saw back in 8th grade and 9th grade. Let's move into something that's a little bit more useful, specifically the kinematic equations. And there are 3 of them that we're going to use a lot of. And each of them have their own unique position to be used in because they're missing something. Velocity here equals initial velocity. Whenever you see a naught, a little 0 at the bottom, so V naught is what this stands for. You saw that on the previous slide with position x naught, initial position, or position at time equals 0. So here's V naught, the velocity at time equals 0, or if you want to say the initial velocity. So V, the final velocity, equals V naught plus A, that's acceleration, times time, t. So that's one of the kinematic equations, and the nice part about this one is it does not involve displacement or position. So if you don't know any information about a position or the displacement, a distance, if you will, to simplify it down, of an object, then this is going to be your kinematic equation here. If you don't know final velocity, then this one's going to be great. I have final position equals initial position. By the way, if I subtracted this to the other side, x minus x naught, that's final position minus initial position, that would be a displacement. So final position equals initial position plus initial velocity, v naught, times time, plus a acceleration times time squared. And there's actually a mistake here. There's a typo. This should say 1/2 AT squared. So please make sure to correct that. That 1/2 is very important. And once again, the advantage with that equation, no final velocity. So if you don't know anything about the velocity ends up at, you make sure to use that equation. Here we have final velocity, but time is not involved. So if we don't know anything about time, this one, final velocity squared equals initial velocity squared, v naught squared, plus 2 times the acceleration times, make sure you realize the parentheses there, final position minus initial position. If you so chose, you could condense final position minus initial position to be delta x, or change in position, which is a displacement. Alright, so I'm going to work 2 quick example problems for you here using these kinematic equations. The first one, I've got a car accelerating from a red light. There's its acceleration, rate of acceleration, 3.9 meters per second squared. Meters per second squared is the unit for acceleration. We should go ahead and point that out. The units for velocity is meters per second, and that comes from just base units of displacement or distance and time. The base unit for displacement or distance is meters, and the base unit for time is seconds. So whenever you're using acceleration, meters per second squared, a reason for that is it's a change in velocity divided by time, and velocity is meters per second squared. So if you go back to your basic equations, trying to think through these units here, velocity equals a distance or displacement, meters, divided by a time, seconds. All right, so you have meters per second for velocity. Now, acceleration is change in velocity over time, so that's meters per second divided by seconds. That's how we get to meters per second squared. Moving on from that, though. In this problem, how long does it take the car to accelerate up the ramp? All right, so let's work that out very quickly. I went ahead and I drew out a picture. Now, I should point out with your pictures, don't ever worry about how good they look. They're going to look hideous for most of us, and that's perfectly fine. Draw them anyway. Just the act of drawing them and thinking through it is going to help maybe open your eyes to how to solve the problem. So you'll see that my drawings are terrible. Please don't spend much time on your drawings. You have more important things to do. So here I've got a car. I know I'm going 45 meters. I know my acceleration is 3.9 meters per second squared. And implied by the fact that we were at a red light, my initial velocity is 0. So now I'm going to write down everything that I know and what I'm looking for. All right, so writing down everything that I know, I'm going to set the initial position of this car to be at 0 meters, which makes logical sense, and the final position of this car, going over the entire length of the ramp, 45 meters away. The initial velocity, because we were at the red light, 0 meters per second. We have an acceleration, a positive acceleration of 3.9 meters per second squared, and we're looking how long, so we're looking for time here. Another point that I need to make about solving these problems, almost every physics problem, I probably should have integrated this back into how to solve a physics problem back in that video. You need to pick positive and negative directions in pretty much every single physics problem, and then stick with it. It doesn't matter which way you pick as positive and negative, that's up to you. You just have to pick it and you have to be consistent. I'm calling everything to the right on my picture positive and everything to the left on my picture negative. And it just so happens that the car is going forward to the right, 45 meters, accelerating to the right, so I can call that positive 3.9 seconds. Now, looking at these equations, or looking, excuse me, at these variables, I know exactly which kinematic equation to pick. It's going to be x equals x naught plus v naught t plus 1/2 at squared. So now let's substitute into the equation. And now we can go about solving. Before I do want to point out something about this equation here. So our initial position was 0, leaving this entire term to be 0. Our initial velocity is 0 as well, which means this term here, this v naught times t, is going to completely cancel out. Word of warning though, that will not always happen, especially in deceleration problems. That won't happen at all. So you'll have some number times t. In fact, if you look at this entire equation here, this is a quadratic equation, so where you're going to actually have to use the quadratic equation to be able to solve it if you have some term in here for v naught, if there's some initial velocity. So you would want to subtract this guy over, set him equal to 0, so then you could use the quadratic equation nice and easily, but in this case it doesn't actually matter because this entire term cancels out because 0 times anything is 0, so that 0 times t completely goes away, leaving me with 45 equals 1/2 times 3.9 t squared, and let's solve for t. And I come out with an answer of 4.8 seconds. Notice I went ahead and put on units. Time, base units is seconds, and I already checked for significant figures here. I have 2 significant figures in 3.9. I have 2 significant figures in 45. There are no other given numbers that I have to deal with in the problem. The smallest number of sig figs given is 2 because it's consistent there, so 2 sig figs go into my answer. All right, next problem. So let's let a deer step out 65 meters in front of a car traveling at 22.5 meters per second. By the way, 3 sig figs. If the maximum deceleration of the car is 4.8 meters per second squared, 2 sig figs. Will they hit the deer? So this is going to be a comparison problem. Okay. By the way, since I have 3, 2, 2, and this actually isn't going to go into my calculations, and you'll see that here in a minute. You always go with the least number of significant figures, meaning that 3, 2, I'm going to end up having 2 numbers in my final, or 2 significant figures in my final answer. So here I drew a little picture for us, and now I'm going to write down everything we know and what we're looking for. All right, let me point out a few things about what I just wrote down here. So I set my initial position to be 0, and I am actually going to look for what the final position is. Let me explain why. The question is, will they hit the deer? Will the car hit the deer? Not how far will the car travel, at what speed will it be going at 65 meters. It's simply, will the car hit the deer? So we need to set up a comparison. If I solve for how far the car ends up traveling using its maximum deceleration, I can compare that to 65 meters. If the car is able to stop in a shorter distance than 65 meters, then we're fine. The deer lives, the car doesn't get messed up, the people are happy, the deer is happy, all is well with our world. On the other hand, if the car goes exactly 65 meters, well, we're kind of cutting it close, we might bump the deer. And if we go further than 65 meters, well, that's not so hot. So this is a comparison problem. That's why I'm going to solve for the final position here. I have my initial velocity at 22.5 meters per second, and let me point out this thing in particular on the acceleration, the negative symbol. Here's why. We are decelerating. If I call to the right positive, which I defined already that to the right had to be positive because my initial velocity was going to the right, 22.5 meters per second, so to the right according to my picture. We are not accelerating to the right. We are decelerating. That means we're accelerating back to the left, because accelerating opposite the direction of the velocity is the same thing as decelerating. They're exactly the same thing. So let me restate that. Decelerating is the exact same thing as accelerating the opposite direction of the object's velocity. One way or another, pick your positives and negatives and stick with it. Deceleration oftentimes is considered negative, just based upon directions there. So because velocity was going to the right, positive, acceleration was deceleration, going back to the left had to be negative there. And I'm looking for when the car comes to a rest. That's the next part of this problem here. I'm wanting to know, I want the car to come to a stop. I don't want it to hit the deer, so I'm hoping that the car comes to a stop in a shorter distance than 65 meters, but I don't know for sure. So I'm going to solve for how far the car is along whenever it comes to a rest. Now that's a couple of points that you do have to take in here. This idea of a car coming to a rest, that wasn't stated in the problem. That was just set up. That's kind of implied. You have to think about that. This is a comparison problem, so I'm going to solve for final velocity and compare to, solve for final position and compare to how far the deer is away. So now let's pick an equation. Now notice in my variable bank, which by the way, this is why a variable bank is so important. Draw a picture, write down everything you know, write down what you're looking for, and use that to pick your equation. Notice that in my variable bank, I do not have time. So I picked the kinematic equation without time. Now, it's what we call plug-chug math. It really doesn't take any effort or thought. I substitute in numbers, and I work the algebra. And I come out with a final position of 53 meters away, so that means that we stopped in time. We were able to reduce the velocity all the way down to 0, stopping, in 53 meters, short of our 65 meters, and the deer lives. All right, guys, we're going to stop here for now, and then Tuesday you're going to come in, or the next class day you're going to come in, and we're going to try to dig into these kinematic equations a little bit more. Please bring your questions. Make sure you have taken great notes. That's your homework, to show me that you have great notes over this. And we'll get started on this here in our next class period.